I have to touch upon real quick, when you were talking about robotics and assemblies and everything, it almost sounds like you're talking about a form of computational alchemy, if you would, in the modern sense.
Yeah, it's a good term for it. Yeah, yes, I think that's right. It's a nice term, actually. I mean, that term, it's the alchemists were concerned with, what can you make from, can you make, gold from lead and things like this, and this is kind of, can you make anything from that computational substrate? Yes, I think that is and that's, one thing we've already learnt in computation, in our computers, we can pretty much make anything in our computers. And now the question is, can we translate that into making anything out of atoms and molecules and so on? And the answer, I'm sure, will be yes. Now, then the question is, will we discover we can do that right at the time when we decide, well, actually, our experience is better had in a purely virtual domain, so to speak. In other words, the implementing our experience with actual atoms and molecules and physicality is something that might not be the final story, so to speak. I mean, in the end, everything has a physical substrate, but the question is the stuff that we care about part of that physical substrate? And I think we already know that, minds are not the same as brains. A mind is something that has a more abstract concept than the physicality of a brain. And so, this question of sort of how do those peel apart is interesting. But I think for the time being, yes, I think it's a good term, computational alchemy, for what I think is possible to do, what one can expect to do in the world, and sort of to create whatever physical forms one wants.
Go on.
Yeah, please.
Oh, just in order to manipulate those underlying substrates, it kind of sounds like we're going to require some fundamental theory of physics. And if we can achieve that, then once we start to know more of what's actually going on within those underlying substrates, I mean, at that point, I think that solves a lot of problems within humanity that we have. If people didn't need to worry about where their next meal was coming from, and we could focus more on just actually interacting with other human beings, getting back I would love it to be back just like the mimetic of the past of Socrates is walking down the street and somebody would say, Socrates, well, what about this? And they would have some dialogue, and rather than just focusing on just like getting all the resources, trying to maximize our return on investment and everything like that. And I understand that's totally a thing. It's going to be like that for a while. But if we could actually focus on actually maybe exploring the cosmos, diversifying the planets on which humanity exists. Just because I remember back in 2019, they gathered a whole bunch of really smart folks and had them run two extreme drills. One was a pandemic, one was a space rock. In those simulations, we failed both of them miserably. Now, it seems like real life kind of played out. We didn't handle one of those very well. The second one, I'd rather not get to that. I'd rather not have to deal with a space rock. I'd rather have us actually be able to focus on exploring the cosmos, because I think that would just be just a new era for humanity. And get people excited, because humanity, we really need a win, I think. And hopefully the Wolfram Physics project can kind of help us with this, just because it makes a lot of sense to me, in that I actually just started understanding yesterday in your live stream what the concept of rulal space. I had heard it. I'd heard all these different things. I'm like, oh, it's just the perspective of there are these underlying rules and everything. And again, one of the things you noticed in NKS was that apparently within cellular automata, you only have primarily 4 real kind of almost categorizations of what's going on. And you think about all the potential rules you could have, but they tend to trend in those 4 particular ways for each unit of computation. It didn't need to be that way. So that's why when I saw you and then I saw Jonathan modeling like black hole merges and everything, I'm sitting there, I'm like, this young man is a wizard. He's literally doing computational wizardry, technomancy, if you would, in that you can actually start to visualize these in different ways. You have causal graphs, you have just all the different forms, and then you propose the whole concept of the Roolead. I'm like, The professor is throwing down. He is literally just going to the point where, okay, I'm going to attempt to do everything, which kind of harkens back to one of perhaps your mentors, Professor Richard Feynman's concept of Feynman diagrams. We're just going to compute pretty much everything, see the most plausible routes, and see if we can figure out what's going on. And maybe you could kind of just touch upon quickly just the concept of hypergraphs and kind of how you've taken that step from cellular automata within NKS and applied it to the hypergraph realm.
Right. I mean, sort of the key idea there is, what is space made of? And it's sort of a funny thing that go back to the 1800s and people were still arguing, what's water made of? Is it just fundamentally continuous, or is it made of stuff? And it took until the early 1900s for people to realize, yes, water was made of discrete things, molecules. And then actually it was Einstein who first sort of said, well, what about the electromagnetic field? Maybe light and everything about electromagnetism is also made of discrete things, photons. But people never quite got the idea about space. Is space made of discrete stuff? And that's sort of the starting point for our physics project, is space is made of discrete stuff. Space is made of these things we call EAMs, atoms of space. And the only thing that one can say about these atoms of space is how they're related to each other. And the way to represent that is with a graph or a hypergraph that represents the relations between all these different atoms of space. And so just like in the case of something like water, got these molecules bouncing around underneath, each molecule just knows how to bounce off other molecules. But when you look at the aggregate behavior of those molecules, it follows the equations of fluid dynamics. Well, what happens when you look at the atoms of space and you see what they're sort of, as they evolve and change this hypergraph and so on, what is the aggregate behavior? It turns out the aggregate behavior seems to be Einstein's equations, the equations for the structure of space-time. And so Jonathan actually just recently, I think he just sent me this a few days ago, and I think it isn't finished yet, but it's his latest effort to really go from this hypergraph that represents the structure of space and see what that implies for the sort of large scale structure of space-time and for things like black hole mergers and so on. And what's really kind of cool about that is what we really need to find, we need to find the Brownian motion of space. So in the history of kind of studies of matter, people didn't know molecules existed. What was the evidence molecules existed? People said, well, it might be discrete. We don't know how big the molecules are, et cetera, et cetera, et cetera. But there was this phenomenon, Brownian motion. Put a little tiny pollen grain in some water, it gets kicked around. You can see that under a microscope. A guy called Robert Brown saw that in the 1830s under a microscope. Didn't know what caused it. Nobody knew what caused it until about 1900, when people realized actually it's molecules in the water kicking those pollen grains. And you're seeing the fact you see those individual discrete kicks is a sign that water is made of discrete stuff. So, the scales worked out so that you could actually observe that just looking through a regular light microscope and so on. You could observe kind of the atoms of matter, so to speak, the molecules of water or whatever else. So now our challenge is, can we observe the atoms of space? Can we find a phenomenon in the universe that is like Brownian motion was for material substances, that reveals the atoms of space? So normally when people try and simulate black holes, things like that, they start off from these continuous differential equations, things like that. They try to put them on a computer, they have to discretize them. If something about the discretization matters in the answer they give, they say, drat, there's something wrong with our numerical scheme. For us, because we're working sort of from underneath up, we start with this discrete structure of space-time. If there's something at the top that happens about these black holes or whatever else that is affected by that underlying structure, we say, fantastic, because we're then seeing, it's like a microscope letting us see down into the atoms of space. And so the things Jonathan is doing, for example, looking at actual sort of black hole mergers, things like this, actual structure of rotating black holes, things like this. As soon as if we can see things there that are kind of things that are affected by that underlying structure, then one has the potential to just go out. And my guess is, okay, that just like with Brownian motion had been known for basically 100 years. at the time when people realized this is a sign that matter is discrete. My guess is there's a phenomenon that's been known a long time, which once we untangle it, we'll say, oh my gosh, that should have shown us that space is discrete, should have shown us 50, 100 years ago that space is discrete, but we didn't know how to interpret that phenomenon, and now we do. And actually my best guess, my current best guess is dark matter is that phenomenon. It's been known for 100 years that galaxies, the rotation of galaxies, is not what you would expect based on the gravity of the luminous objects that we can see in galaxies. And the question is, what else is there? And it's, my current feeling is, if you look back at the history of studies of matter and so on, one of the big mysteries for a long time was, what is heat? Is heat some fluid, some substance that sort of suffuses matter? And that was the prevailing theory. The caloric theory of heat was the prevailing theory of heat. That's where our term calories comes from. But caloric meant the sort of the characteristics of heat that are not part of matter, that are just this thing that is heat, that isn't matter. And people didn't understand. It took until the 1800s, towards the end of the 1800s, before people understood that, in fact, heat wasn't a separate substance. Heat was a characteristic of motion of underlying molecules in an existing substance. And so similarly, my guess is that dark matter, people currently, they're off searching for particles of dark matter and things like this, because particles are what we know. Everything we know of is made of particles. But actually, it might not be that way. It might be that dark matter is a feature of the structure of space that isn't something that can readily be thought about in terms of particles, just like heat is not something that is readily thought about as a fluid. It's a different kind of thing. It's a different it's a different sort of instance of matter, not a different kind of matter, so to speak. So anyway, I'm kind of, one of the things that is sort of the big challenge, I would say right now, is one of the challenges with the physics project specifically is what are places, what are sort of actual things we can measure out in the world that show us that physics really works this way. I have no doubt this is how it will turn out. I mean, there's just way too much is fit together for this not to be basically what's going on.